is the link for it. But
ঠিক আছে, তোমাকে মাইক্রোফোনের পারমিশনটা দিয়ে দিচ্ছি।
Issues for the past.
শ্রাবন্তী, তোকে আমি মিউট করছি তাহলে।
নাতাশা, recording of the session which will be uploaded later.
মিউট করিস না, নোটিস একটা ওয়েট।
In case of any inconvenience caused in between in the streaming, we assure you there will be a recorded session which will be uploaded later. Inconvenience is regretted. হ্যাঁ বলছিস না, আমি না সিমরানকে আমি অডিও দিলাম। ও আচ্ছা, হ্যাঁ হ্যাঁ বল। দেখা যাচ্ছে না শুভজ্যোতি কোনটা
এসছে কি? দাঁড়া দাঁড়া,
তোমাকে আমি এন্টার করাচ্ছি, তুমি এটা এখানে বলো। ওয়েট করো ভাই, একটা প্রবলেম হয়েছে, ওয়েট কর। ঠিক আছে ঠিক আছে, আমি তোমাকে এলাও করতে বলছি। শোন, প্রতীকদা স্ট্রিমিং করতে পারবে না। কেন? প্রতীকদা, তুই শুভেচ্ছাদিকে এলাও করেছিস?
হ্যাঁ করেছি।
শুভেচ্ছাদির মাইকটা অন কর। ওই তো। হ্যাঁ, কেন প্রতীকদা পারবে না কেন?
আহা, দিদি করুক না এখন,
সেও দিকে করবে। সুনন্দনকে বল।
ও ঠিক আছে,
আমরা apologize করছি in advance. বলে দিচ্ছি we will try our best, but কিছু টেকনিক্যাল ইস্যু হলে একটা রেকর্ডেড সেশন পরে আপলোড করা হবে। এরকম ভাবে মেসেজটা লিখতে বলেছি। হ্যাঁ, আর সুনন্দিনীকে কেউ একটুখানি ফোন করে শ্রাবন্তী সুনন্দিনীকে বল ব্যাকআপে থাকতে।
সবার ভয়েসগুলো মিউট কর, আমাদের ইউটিউব লাইভে ভয়েস শোনা যাচ্ছে। আমি আমারটা মিউট করে দিচ্ছি, ঠিক আছে? সুনন্দিনীকে বলে দিচ্ছি আসতে।
হ্যাঁ, কল করে সুনন্দিনী আছে, ওকে জাস্ট বল যে ব্যাকআপে থাকতে স্ট্রিমিং এ সবকিছু ফিক্স রেডি রেখে।
দাঁড়া আমি স্যারকে ফোন করছি।
লাইভ স্ট্রিমিং করতে পারবে না, তাই তুই তোর সবকিছু রেডি করে ব্যাকআপে থাক। ওকে, তুই ব্যাকআপ আমাদের আছে, দরকার হলে পরে রিচার্জ করিয়ে নিবি, এখন করাস না। লাইভ স্ট্রিমিং করতে পারবে না, তাই তুই তোর সবকিছু রেডি করে ব্যাকআপে থাক। ওকে, তুই ব্যাকআপ আমাদের আছে, দরকার হলে পরে রিচার্জ করিয়ে নিবি, এখন করাস না।
হ্যাঁ স্যার,
এলাও কর।
বলছে ইয়ে করছে।
এই
সবাইকে
নামগুলো নোট কর। সুজিত ত্রিপাঠী, সন্দীপ রয়, সঞ্জীব নন্দী, এমএল দোরা।
10:30 বেজে গেছে, সবাইকে লেটেন কর।
এরা বিটিএইচ এর টেস্ট, এদের খেলাও করে দিস আগে।
এই শ্রাবন্তী তো মিউট করবো না?
আমি মিউট করে দিচ্ছি।
তো ভাই 10:45 এ কিন্তু একদম স্টার্ট করে দেবো, তাই তো?
10:30 বেজে গেছে।
না না, আমার কথাটা শোন, 10:45 ডট ঘড়ি ধরে আমি স্টার্ট করবো তো। শোন, চেয়ার স্যার এসে গেছে কিনা আমাকে তুই, আমি কাউকে একটা এই গ্রুপে অ্যাড করে নিচ্ছি, ফাইনাল কোশ্চেন সে আমাকে জাস্ট জানিয়ে দিবি, বা আমার হোয়াটসঅ্যাপে জানাবি। কাকে?
আমাকে।
ওকে ওকে ওকে।
সুনন্দিনী ফোন কেন তোলো?
লেটিন করছি। আচ্ছা,
হ্যাঁ কর।
নাতাশা
লেটিন কর।
হ্যালো,
করছি।
আছে
হ্যাঁ স্যার স্যার।
আমাকে দেখতে পাবেন, ওকে পাচ্ছ কি না?
ইয়েস স্যার।
আচ্ছা, আমি কি এখন তাহলে তো আমার ওই ফাইলটা ছিল, এখন তো অন্য জিনিস হবে।
ইয়েস স্যার।
স্যার হ্যাঁ স্যার।
ওপেন শেয়ার মেনু দেখাচ্ছে, আমি
থেকে
কিছু
শুরু
করবো?
হবে।
আচ্ছা শোনো, আমি
না
কি
স্যার,
ওপেন
এখন
শেয়ার
থেকে
মেনু কিছু করবো না তো? ঠিক আছে।
participation, or else your questions won't be accepted. The link of the feedback form for this webinar will be shared in our Telegram group. At the end of second lecture, around 4:30 p.m. today, I request all the candidates from different universities and organizations to fill up the feedback form. Otherwise, will not be able to issue certificates. Now I welcome Dr. Jyoti Shankar Roy, sir, our head of the department, to give welcome speech for this webinar. If sir is there? Obipsha?
No, sir hasn't come. Please wait 2 minutes.
Okay, let's wait for some time, for 2 or 3 minutes. Sir will be with us shortly.
So,
হ্যালো আচ্ছা আমি তো ঢুকে গেছি তোমরা তো কিছু দিচ্ছ না
yes, sir, you are audible.
asking me to
Sir, you are
download any
audible.
audio and video
Yes, sir, you are
Hello.
audible,
Sir, you are
sir.
audible.
yes
Sir,
So you can
please turn on your camera.
hello
Hello. Yes, sir. Now I welcome Dr. Jyoti Shankar Rai, sir, our head of the department, to give the welcome speech for the webinar. Sir, over to you.
hello I am audible can
Yes,
you
sir. Yes,
can
sir.
you can you see me all okay
Yes, sir. You are
I cannot
audible.
see you.
okay a very good morning
Sir, your face is not in the screen.
I cannot see anybody.
Okay. Camera is there, but maybe my voice is audible. That's all. I should be always behind. I mean, due to some reason or other, face is not appearing. So I don't know something. Something has happened maybe with the camera, but that doesn't matter. If you can all hear to my talk. I mean,
Yes, sir, you are audible.
Okay. If I'm audible, no issue. So I think very soon I'll be able to show my face as well. That's not important in this stage now. But I should appreciate all the third semester students and other students of our department that during this special, I mean, very peculiar situation, I should say, that during this pandemic period, they have found a academic forum which is known as IGNITE'20, just to have academic interactions amongst the teachers, among the students themselves, and also along the research scholars. And I think this webinar will be their first attempt, as we are asking, and I am very happy that this platform IGNITE'20, the student platform, they have arranged this webinar today on this particular day, auspicious day, 5th of September. And I should welcome all of you who are participating in this webinar today. And I should also acknowledge the kind gesture shown by them to all of us, the teachers, students, research scholars. And the special thanks are therefore to speakers of today. One is our Professor Tapas Bhattacharyya, Tapas Da, who will be speaking on some intricacies and fun of plate tectonics. I think that is in the first session, which will start just within 5 minutes from now. And the second speaker after the recess would be our colleague Dr. Vishwajit Ghosh. He will be speaking on some aspects of mantle melting, how and where. So with this much of introductory speech or introduction where my face is not visible, no problem. I would request all my student friends, especially the coordinator, Dipomal, I think, to initiate this webinar session, where the first speaker will be Professor Tapas Bhattacharyya. So I hand over my mic to the students coordinator. Thank you all.
Thank you, sir, for the welcome speech. Okay. On behalf of all the participants and my colleagues, I welcome our beloved sir, Dr. Tapas Bhattacharya, in this webinar IGNITE 2020. It is our pleasure to have him amongst us on this auspicious day. Dr. Tapas Bhattacharya is a renowned name among the Indian geologists. His area of expertise includes structural geology, tectonics, and Precambrian geology. Dr. Bhattacharya has published numerous research papers working with professors and research scholars from different universities and organizations across the world, including Presidency University, University of Southern California, University of Queensland, Raman Center for Applied and Interdisciplinary Science, West Valley College, Jadavpur University, and many more. His researches are regularly published in national and international journals like Journal of Structural Geology, Journal of Structural Geology, Tectonophysics, Journal of Geological Society of India, etc. His remarkable works related to Nevadan orogeny in California and South Delhi Fold Belt in central Rajasthan is deeply appreciated by geologists worldwide. Recently, he has authored couple of research papers on Bundelkhand Craton. He received awards from Asiatic Society, National Science Foundation of Washington, UGC, Geological Mining and Metallurgical Institute of India for his excellence. As a professor of geology, Dr. Bhattacharyya has served many institutions, namely Ashutosh College, University of Allahabad, Florida State University, and University of Calcutta. At present, Dr. Bhattacharyya gives lectures on geodynamics and geomathematics at University of Calcutta. It is a priceless opportunity for the students to learn from him. I am sure you all are going to love this session of IGNITE 2020 with beautiful presentation by Dr. Tapas Bhattacharya to tectonic plate movements. Fun with plate movements vector. Now, I would request our respected sir, Dr. Tapas Bhattacharya sir, to say a few words before the session begins. So, over to you.
Thank you, dear students, for giving me this opportunity to present this talk. It's a very kind of new experience for me. I'm quite used to talking in a class with at least 20, 30 faces looking at me, and I can judge their responses. But this is something possibly I'll be reaching many more people without seeing their faces. That's a new experiment, but possibly this is the only way to go from here now. It's a very special day, Teachers' Day, and I take this opportunity to offer my respect to all my teachers at very many different levels, starting from my childhood till today. I learned from them a lot. Possibly I should have learned more. And even those people who did not have me in their classes, I owe a lot of them. A lot more, because I tried to emulate them. Whether I could or not, that's a judgment made by you. And I must mention, among the teachers, I include the parents, because who are our first teachers ever, who teach us how to live. Now, I think I can go straight to the talk material, and let me project the slides. The topic, as has been mentioned, is fun with plate movements. That means movement of plates on the surface of the earth. And here, with the plate movements, I have added something else called vectors. So this is fun with plate movement vectors. When we hear, most of us, the word vector, the picture that flashes in our mind is that of an arrow. And that is exactly what vectors are. It has a body, linear, straight, with an arrowhead. The vector quantity has a magnitude that is given by the length of this body, this straight line. An arrow gives the direction in which the quantity is applied. So it is a perfect example of a vector is an arrow. Now, this arrow is directed from one direction to another direction. That is what exactly is meant by velocity, because the simplest example of velocity is an arrow. It has a magnitude, say 10 kilometers, that is the length of this body of the arrow, and 10 kilometers to say north, that gives the direction. So to us, vectors, arrows, and velocities are practically synonymous. And what happens when the plates move? It's related to the vector along which the plate follows. It moves from one point to another, and which vector it is following, that is the important aspect of plate tectonics. The essential character of plate tectonics is relative movement between two plates. Yes, please.
Sir, the slide is not changing.
I am not changing it. Okay. Sure.
Okay. The participants were confused. Okay, sir. Thank you, sir.
No, because I am giving an introduction, so it's okay. Thanks for reminding me. So when the plates move, there is a movement between neighboring plates. That is the essential character of plate tectonics, relative movement between the plates. And we use the word relative velocity, that is velocity between A plate and B plate. We are not concerned about, in the statement, velocity of A plate with respect to B. What is the movement with respect to a fixed point? In plate tectonics, we also use a word or phrase called absolute velocity. What it means is that the velocity of a plate, irrespective of its velocities with respect to the other plates, the velocity of the plate with respect to north geographic pole. In this presentation, I will address the problems and nuances of these relative velocity vectors. One other reminder, Earth is a sphere. That means it is a curved surface. So when plates move, plate must be moving on a curved surface. So their movements will be around curved lines. And when you make things move around curved lines, they move around an axis. We call that axis of rotation, or also called Euler poles. Now, when you are moving plates on the surface of the Earth, this is a three-dimensional motion. Then what is the use of using two-dimensional vectors? The interesting aspect of Earth geometry is that it is a sphere of a very huge radius, 6,000 plus kilometers. So when you look at the surface at the scale of, say, 100 by 100 kilometers square or even larger, for all practical purposes, we can take it as a two-dimensional planar surface. And these areas are very important sizes when we consider the boundaries between the plates, where the actual movements are taking place. So using two-dimensional vectors in planes, we can solve problems of plate movements. And this is what I am going to present. The other aspect of this plate tectonics is that plates move. And this is how we analyze it. I have shown an area which is a plane. It's a geographic surface with north going in that direction, east in east, west. So this is a geographic plane. Whenever I plot 2 points in this space, we call it a velocity space, it gives you two information. And it says that there is a relative velocity between A plate and B plate, represented by points. This can be two individuals, it can be two trains, two shapes, anybody, but they'll be represented, as long as they're moving with respect to each other, they'll be represented by simply two dots. Okay, why are they giving me these trail marks? Should not give me the trail marks. Is there any way to get the trails out?
Yes, sir. I am undoing it.
Okay, fine. Do it. Thank you very much. Again, it is giving the trail marks. Can you take it off the trail? Okay. So let me continue.
Sir, have you enabled that?
No, I did not enable the trail thing. I check it. Oh, enable trail. Okay.
So there's an eraser which you can use.
Okay. So when I plot 2 points A and B, they represent two moving objects. Could be size of continents, could be individual. The information it conveys to us is that there is a relative velocity between the point A, and in plate tectonics, I'm taking it as a plate A, and plate B. It also gives us the other information that the relative velocity is given by the distance, the magnitude. In plate tectonics, we take it the distance covered in unit time and measure it in millimeters per year or million years, 10 to the power 6 years, kilometers per million years, 10 to the power 6 years. So this gives a magnitude. As long as this velocity remains constant, this velocity space remains constant. Even after 20 million years from now, As long as the velocity remains constant, that is the magnitude of this distance, and the second component, the direction, the velocity space will remain the same. But in actual or geographic space, the 2 points, the 2 plates will be changing the distance between them. The other quantity of the vector is that it fixes in which direction B is moving. In this diagram, B is moving to a direction of 55 degrees with respect to north, with a velocity equivalent to this distance. And we call it velocity of B with respect to A, and represent it by AVB. We can think in the other way. The plate A has a velocity such that it is moving to the southwest, that is 235 degrees with respect to B. Note, we are not mentioning the relative positions. We are mentioning only the velocities. So in the other way, we can talk that BVA is the same amount as ABV, but now A is moving towards 235 degrees. This is all there to it regarding the relative velocities. Some textbooks and author puts an arrow. When I am showing it there, I am not putting an arrow, and this line is simply called the velocity line, the line along which plate A and B is moving relative to each other. When you see an arrow plotted at there, it implies the author wants to keep A fixed, not moving. That is, I am taking it the origin of this two-dimensional space. And the other choice is that you can put B at the origin, keeping it fixed, so that the A will be moving towards 235 degrees, keeping the B constant. Knowing the relative velocities is just one step in understanding the geology that is resulted by plate tectonics. And we look at the next slide. If I look at the next slide, I have shown you here 8 small areas, 8 boxes, numbered 1 to 8, with the velocity space zone. This is, each box is giving you a true space that is geography. And here it shows the relative geographic positions of the plate A and B. These diagrams are grouped according to 2 parameters. One, what is the boundary between the orientation of the boundary between A and B plate? And there is one set of diagrams that shows they are perpendicular to the velocity line. The velocity, that means the line along which A and B are moving relative to each other. The other extreme variation is that the plate boundary, represented by dashed line AB, is exactly parallel to the velocity line. And the third category is that they are neither parallel nor perpendicular, but showing different angles with respect to the plate boundaries. This is one parameter. The other parameter is a very interesting one. If you look at the top row, you see what is happening here. Here, the B plate occurring with respect to A in the same direction as the relative velocity of B with respect to A. You see here B is moving to northeast 55 degree with respect to A. In this set of diagrams, we will see B is occurring to the northeast of A. If you look at this set of diagrams, it is just the reverse. So we'll look at the first few row of diagrams and see what is expected of this. When B is moving to northeast with respect to A, and A is moving to southwest with respect to B, parallel to this line, these will be the direction of movement of these 2 plates. So you see, the B plate is moving away from the plate boundary, So is the A plate. So it will be a rift. A rift, like the mid-oceanic ridge between A and B plate. Even if I look at these two situations, these will be also rifts. But the difference between these two are, here the rift is spreading orthogonally. That is, the velocity of B plate is exactly perpendicular to the AB boundary. Same is the case with A plate. This is not the case in either of these two. Here the velocity is oblique to the plate boundary, though both of them are rifts, so we call it oblique spreading. On Earth, more than 90% of these rift boundaries for geometrical reasons of stability are orthogonal. And the velocity of B plate with respect to the rift is exactly similar to the velocity in magnitude. The magnitude of the velocity of A with respect to the AB plate. So in each case, wherever it is parallel, perpendicular to the plate boundary or oblique to it, it is the same situation, and this is called symmetrical spreading. In the rift, material is added by equal amount on two sides. Now we come back to velocity space and explore a situation where we call it a true space. We have seen the true spaces. These are the true spaces, and let us pick up this true space. In the true space, the situation is I have plotted A and B and the velocity line, and like the previous first diagram, the plate boundary is a rift. And when you plot the plate boundary on the velocity space, we plot it as a dashed line and name it in small letters AB. Some people put them in italics. So this is the message conveyed by the situation where A and B plates are separated by a rift with this is the velocity space. This is all you need to explain that. Note what is happening, because it is symmetrically spreading. It is passing through the middle of the velocity line, and we are transferring the orientation of the plate boundary exactly in the true orientation as we see in the true space, in the velocity space. So it is running northwest, southeast. So it is a rift, orthogonally spreading, because the velocity of A plate is to the southwest and it is to the northeast. Now this is the point where the rift intersects the velocity line. You will recall, as I said, that any point plotted on a velocity space will have a velocity with respect to the other points plotted in the velocity space. So there is plate A plotted, there is plate B plotted. Now we are plotting the point rift here, R. So R has a velocity. What kind of it is? R is moving northeast at this rate with respect to A. So we call it AVR. And again, B is moving to northwest with respect to R. So we call it RVB. This AVR and RVB are called half spreading rate, because the true velocity between A and B is the entire length. And half spreading rate means half of that velocity. That is, if we keep the rift constant, A will be moving, B will be moving away by this amount to the northeast, and at the same time, A will be moving away. So this is half spreading. And if you look at the magnitudes, AVR and RVB, they are the same. And if you add them just vectorially, you cancel these two words and it becomes AVB, that is the full spreading rate. Let us look at a real life scenario. Rifts are very common in mid-oceanic ridges. We have two plates. This is north in 3D. This is a green plate. This is a blue plate. And they are orthogonally spreading. That means from the boundary, this is the rift boundary, the green is moving to the east and the blue is moving to the west. And we see the same scenario here, but interestingly, there is an offset of this rift, and this offset is a dextral rift offset. What it means is that if you walk along the rift, move towards a direction, to follow the rift, you have to quite often move to your right. So we'll talk about it more later. So this is the true space scenario of a rift boundary between two plates. So now we come to the second set of examples, that is this one. The velocity line remains the same. The velocity space is the same. So the relative velocity AVB is the same. But even the plate boundary is perpendicular to the velocity line, but the plates have switched places. A is now occurring to the northeast. Just that means it is in the direction opposite to its movement direction with respect to B. Because A is moving to the north-southwest, but now A is occurring to the northeast. B is moving to the northeast, now it is occurring to southwest. The same scenarios here, only thing is that the plates and boundaries are not perpendicular. So what will happen? A plate will move to the southwest, this is the vector. B plate will be moving to the northeast, this is the vector. So two plates will come towards each other and collide. This is the scenario commonly it generates what we call a subduction zone, where two plate comes moving towards each other, and one plate goes underneath the other by bending and going back to mantle, and we call it a subduction zone. And this is the scenario of the subduction zone. On the surface of the Earth, a subduction zone is marked by a very deep, long depression. We call it a trench. Trenches are the lowest points on the surface of solid Earth, like the lowest point Challenger Deep in Marianas Trench to the east of Philippines. So the boundary is marked by this dashed line, AB, is a trench. So when two plates converge, there is a subduction zone, and the subduction zone appears as a trench on the surface. You see, we are having subduction zone or trenches which are not perpendicular at different angles, and these are fairly commonplace on the surface of Earth, unlike this situation for rift. This is, I will first take up a scenario, this one. I'll draw a section along this vertical section, along this velocity line. So the right end of the section will be 55 degrees. The left end of the section will be 235 degrees. And it will go perpendicular to the trench. So this is what it is. This one. The trench is perpendicular to the section. So coming out of the stream perpendicular towards you. B plate is towards the west, 235 degrees. A plate is towards east, 55 degrees. But you see, B plate, even if it is in the west, it is moving northeasterly. A plate, even if it is in the east, by the velocity space, is moving towards southwest. So this is the convergent zone, and the small area is the trench. So on the surface, the boundary between A plate and B plate is a trench, which is shown as a dashed line. In the rift, we plotted the rift halfway between the two plates like this in the velocity space. But we cannot do that in cases of trenches. Trench has a very unique property. If you look at the plate B is moving in this direction, A is moving in that direction. But you note, this trench is always attached at the tip of the A plate. So there is no relative velocity between the trench and the A plate. Whereas B is constantly moving. At one point in time, this is here, then it comes here, then it goes down there. So it comes away from the trench, comes close to the trench, and then goes underneath A on the other side of the trench. So A will always carry the trench, or in other words, the trench will be attached to A all the time, and B will be moving towards A. And that's it, all you need. When 2 points in a velocity space have no relative velocities, they will be plotted as one. So we take that range. This is the true orientation in the map, and true orientation of the range is perpendicular to the velocity line, and put it on A. Why? Because it is attached to A and there is no velocity between A and the range. So this AB, which is a range, is passing through a plate. So whenever in this kind of diagram, where you are putting a plate boundary on a velocity space, if a boundary passes through one of the plates, you know that plate is a part of a subduction, which is the overriding or upper plate, and range is attached to it. And the subduction is going underneath this plate. So we go back to this planned diagram, and this is what it is shown. The velocity line is like that. AB is a range attached to A, passing like that, and it's a range attached to overriding or upper plate A, B subducts under A. When you go to the other extreme situation, where the velocity vectors are the same, A is occurring to the northeast, just like this, B is occurring to the southwest, just like that. But now A is the overriding plate. So the range will be attached to B plate, and A will be gradually going like that. So in this situation, we'll draw that range as the dashed line AB passing through B. And this is where you are. So this pretty much takes care of the two major kind of plate boundaries when represented on the velocity space, the rift and the range. Let us go to other possibility. Here what we have shown is this one, that unlike in these cases, you can have the trenches. I have shown you only this case, but the trench is perpendicular. But the geometry will be exactly similar, where here the trench is not perpendicular to, or they are oblique to the velocity line. Here it is also. So these are quite common places. And one such important place is right near our home, the Sumatra, the source of the major earthquake, where so many people died in Boxing Day 2004. So these are quite common in nature, where you can see the plate boundary, the range. A is the overriding plate, it is attached to the range is attached to A, but is oblique. So the B plate is going obliquely under it. We go to the final scenario where the plates boundaries, ABs, are exactly parallel to the plate vector. That means the B plate is moving parallel to this boundary, A plate is moving parallel to this boundary. That means it is a strike-slip fault. In strike-slip fault, two blocks of rocks move past each other exactly parallel to the strike of their contact plane. And here this contact plane is marked as the dashed line AB. So these are two situations that can arise regarding these strike-slip faults. Now, we know these strike-slip faults that marks the boundary between two plates are called transform faults, or very briefly transforms. Transform fault has only one definition. It is a strike-slip fault that marks the boundary between two plates. That's it. Quite commonly, we see transform faults across mid-oceanic ridges, but there is no hard and fast rule that all transform fault must be across the mid-oceanic ridges. It can be between two trenches, or it can be between a trench and a mid-oceanic ridge. We'll try to discuss that later. So there is a distinct difference between these two cases. Here we see B plate is occurring to the north. So what is our expectation? What kind of strike-slip fault or transfer will that be? I see the velocity space. B is moving to the northeast. B will be moving to the northeast. A will be moving to the southwest. Both are relative velocities like that. So it will be a dextral transform. Let us see. So this is the velocity line AB. The small AB dashed line gives you the transform fault. And we have B plate in north, A plate in south. B moves northwest, northwest. A moves southwest, southwest. So this is the dextral transform. Look at the other situation where you have A plate on north, B plate in south. A plate is moving according to the velocity space with respect to B to the southwest. B plate is moving to the northeast. So it is a sinistral transform fault or right lateral. And I think you all remember we call it a sinistral or dextral based on your observation. You stand on one block and look to the other block. If the other block moves to the left, it is a sinistral. If the other block moves to the right, it is dextral or right lateral. So look back again at the mid-oceanic ridges. Now we have an added information of these transform faults. So we have already explained the rift, orthogonally spreading. And here we see a transform fault. Note very carefully. The fault exists only between these two ridge axes. This is not a fault because transform fault at all, because to the right of this point, the two blocks have the same plate. A transform fault being a plate boundary, so the transform fault stops here, and the trace of the transform fault fossil appears as a fracture zone. So the transform fault exists only between the crests of the two disrupted part of the reef. Note, the plate here is moving to the right. The offset of the reef is dextral to the right. However, the transform fault is sinistral. Why? I am standing in this wall block looking across the fault and we see it is moving to the left. If we look at the velocity space and put the boundaries there, it becomes very clear. You see, this is the velocity space. Blue plate is to the west, green plate to the east. In between BG, the blue-green is the orthogonally spreading reef. There's no problem. Now we plot the transform fault in again the velocity space. So velocity space-wise, this end is the green, this end is the blue. And now in the particular geographical situation in this plate, we are seeing the blue plate occurring to the north, green to the left. We know the blue plate must move westward with respect to green. So blue plate will be moving to the west and green plane will be moving to the east. So it will have to be sinistral. So this is an axiom. If you have a transform fault along which the rift is offset, if the offset is dextral, the transform fault will be sinistral. Let us test it in another case. You see, everything is the same. Green plate moving to the east, the velocity space is the same. But the transform that exists only between this point and this point is dextral. Why? Now green plate is on the north, so it is moving to the east, and blue plate in the south, it is moving to the west, so it becomes a dextral. And you see, this is a very commonplace scenario. You see along the mid-oceanic ridge, consecutive transform faults have changed from sinistral to dextral. And this is the very meticulous survey map of South Atlantic Ocean. Here, the African plate, which has a boundary, this one. This is the continental part, this is the oceanic part. South American plate, this is the oceanic part of it and the boundary, is moving along an east-west velocity line, and African plate is moving to the east, and South American plate is moving to the west. And you look at it, look at this region. There is consecutive faults. This one is a sinistral transform fault, but the ridge is offset dextrally. But this one, the small one, is a dextral one, and the fault is offset. So you can see they almost alternate like that. There are big places. So this is a very common observation that faults, alternate faults change their displacement because of this velocity space requirements. As I mentioned, transform faults can be also joining portions of trench. And this is a map view. And this is the trench between plate A and plate B. And this is A is moving to the west from the velocity space. B is moving to the east from the velocity space. It is a trench. And in the trench, we put the barb in the direction of deep of the trench. That means B is the upper plate. So what does that mean? The trench will be drawn through B, attached to B. Same scenario here. And the two segments are joined by a transform fault. with the A plate in north and B plate in south. So through B comes that range, the velocity space. AB is parallel to the plate boundary, so it is like the transform fault. And in the north is the A plate, so A plate will be moving to the west. A plate is moving to the west. B plate will be moving to the east. B plate is moving to the east. So it is a sinistral transform fault, and we see the offset is dextral. If we look at the reverse scenario, same velocity space with the same range attached to B, A is to the east, moving to the west. B is to the west, moving to the east. And the fault is dextral because now B is to the north and B has to move east, so it has become dextral. So it is absolutely true that only in the mid-oceanic ridge situation, the transform faults have movements opposite to the offset of the ridges. We look at a more interesting situation where we are having 3 plate instead of just A plate or B plate only. This is a plan view, this is north. We have 3 plates, A, B, and C. A very interesting scenario because we see there is a point here where 3 plates are meeting, A, B, and C. 3 plates meeting means 3 plate boundaries meeting. In general, these points, when you see on the surface of the earth, we call them triple points or triple junction. It is triple points or triple junctions. So now, in the tectonic parlance, more people use the word TJ, that is triple junction. The interesting aspect of this particular scenario, that the plate boundary between A and B, marked by 2 parallel lines, symbol of rift, is a rift, which is geometrically continuous with the plate boundary between A and C. It is also a rift. So it is the same plate boundary as it, going from south to north, halfway through the right plate or eastern plate changes from C to B. It is also showing that the relative velocities of A and B is like that. The magnitude is proportional to the total length of these 2 arrows, which is quite contrast to that between A and C. The velocities, the relative velocities between A and C, it is also east-west. A is moving to the west, E is moving to the east, like here, but it is much small. It is a lower velocity here. Because the plates are moving in that direction, this is a transform fault. This is a common symbol of a transform fault with the movement direction given. We have been given the velocity space here. Though there are 3 plates, it's a straight line. This is in velocity space, means it has a true north mark here, true south here, so this is east, this is west. And for the ease of calculation, we keep the A plate fixed. So A plate is not changing its position. It may be growing, getting distracted or whatever. It is not changing its position with respect to Earth's coordinate. So we make the origin pass to A. Between A and B, B is moving to the east with a velocity like that. So this is the B in velocity space. Between A and C, C is also moving to the east with respect to A, but with a smaller velocity. So this is like that. This automatically predicts that there is a relative velocity between C and B in such a way B is moving to the east with a velocity like this much with respect to C and Y. So if that be the case, and if B is occurring to the west, so this transform a dextral transform. Plate boundaries now on this velocity space. The easiest plate boundary to plot is the plate boundary which is parallel to the movement vector, BC. I have drawn it real bold to make it obvious. So this is the BC plate boundary, exact parallel to the BC vector. Now let us plot this boundary AB, which will be a north-south trending dashed line halfway through AB. So it will be passing halfway through AB, running north-south. This is AB, exactly halfway between A and B. Now, if I keep A fixed, to the earth. What does it indicate? It says as the time passes, the distance between A and AB will increase because there is a velocity of AB to the east by this much amount with respect to A. Similarly, the velocity will give you a velocity with respect to C. It will also move with respect to C in the eastern direction. What about this AC? AC is a rift also, symmetrically spreading, but it has a smaller spreading rate. So it will go halfway between A and C and exactly parallel to the north-south like this. Immediately you come across a very interesting scenario. What it shows that anyway, what it shows is this, that its AC boundary, this one, AB boundary, that one, though it is now as a continuous line, but it is a chance situation. Because with time, because there is a relative velocity of AB boundary with respect to AC boundary, any points on the velocity space indicates a relative velocity to the others. So with time, AB will move away from AC. That means this boundary will move to the east with respect to AC. The other aspect is also very interesting. We see on the surface three plate boundaries meet. But when you plot these plate boundaries on the velocity space, we see no three plate boundaries, BC, AB, AC, are meeting at a single point. That means this triple junction is fortuitous and unstable. Though it is occurring apparently in the physical geographical space, in the velocity space, in the logical space, no three plate boundaries are meeting at a point. So this is not sustainable. We call them unstable triple junction. That means with time, the configuration at the triple junction changes. The nature of the plate boundaries, even the orientation of the plate boundaries changes. So what we expect to see is that with time, there will be a displacement between AB, this boundary, and AC such that AB will be moving more to the east. Here it is. Let us first see what was the prediction. AB will be moving with respect to AC. AB, which was here, because it has a higher velocity with respect to A, has moved by this much, whereas AC has moved only this much. That caused a relative velocity between AB and AC. AB moved much further to the east. Than AC. These hatched areas are the new material added to the plates because of the rifting. You see, it's a smaller amount added because of the slower rate. Very interesting thing that we see is there is a new plate boundary is created between A plate and C plate. A plate and C plate has only a north-south trending rift. Now it has a transform fault which is trending east-west. This is exactly what is predicted here, that AB will be moving to the east. So now take these three plate ABC, plot them again in the velocity space. BC is already sitting there, AB is sitting there, but now there is a plate boundary which is exactly parallel to the AB vector line. So this is shown by these bluish dots AC. So now we have a very interesting situation. Three plates are meeting. Of these three plates, there are three plate boundaries. Two of the plate boundaries are exactly parallel transform faults, BC, AC, and the third one is perpendicular to it. So here, there is a triple junction when you plot the plate boundaries on the velocity space. This is TJ, and this triple junction is stable. So with time, this triple junction is riding on AB. Wherever AB goes, the triple junction moves. Now note, this has to be a sinistral fault. Why? because according to the velocity space, AB is moving to the west with respect to C. So this is a sinistral. So it is a very interesting triple junction we call TTR junction, a sinistral transform, a dextral transform, and the rift. Come to a situation a little more complicated, where the velocity space, the velocity of three plate soles forms a velocity triangle that is more common than the thing that I showed you earlier. We keep the A plate fixed to the Earth's coordinate, so we put it in the origin. This is east. This is 1 millimeter per year or 1 kilometer per million year calibration. T is moving with respect to F, that is FVT, by about 4 millimeters a year to the east. A is moving at around about 2 millimeters to southeast, that is TVA, with respect to T. A is moving with respect to F, again to southeast, of above the order of about 6 millimeters a year, like that, called FVA. Now, the first problem is that what will be the nature of AT boundary? It is running north-south. Now, it's very simple. We see A is moving to the southeast with respect to T, but A is occurring on the northeast. So A is moving in this direction and T is moving in that direction. That means it's a trench. This is one symbol of a trench with a crosshatch, a line with a crosshatch. And if when you know which plate is the overriding plate, then the hatch will be only on this side. Because we do not know which of the plates are overriding plate, to which plate the trench is attached, we make it a cross line like that. The boundary between F and T is very simple. Because the boundary is exactly parallel to the velocity vector, and T is moving to the east, T is moving to the east with respect to F, FVT, this is a sinistral transform. A very interesting scenario appears, which is not very common, but still they happen. The velocity, relative velocity between F and A, that is FVA, A is moving to the southeast. So this is the boundary. FVA moving to the southeast and F moving to the northwest. So it will be a tension zone, a rift, but which is obliquely spreading. This is not very common, but it is true. Now we see the same situation here. Three plates moving at a point, a triple junction, a triple junction. Now the question is that, do we see the triple junction in the velocity space when we plot the plate boundaries here? If we see in the velocity space, when we plot these three plate boundaries, they meet at a point, then we'll say it is a stable triple junction. So let us go to the next set of slides. We see the AT boundary, north-south trending, so it must be parallel to north-south, can be at one of these two places. If
Hello.
hello,
Hello. Sir, there was some problem.
my video is gone.
Sir. Sir, your slide is still there, but you are not visible.
The slide is not, is it visible, the slide?
Yes, sir, it is visible, but it's not changing.
Exactly, it is getting locked here. I can change it here.
Sir.
Again, it is asking permission for audio video. I am giving it.
Yeah.
Yes, I have given it, sir.
It is not changing, okay?
Yes, sir, we can see.
Yeah, it has changed.
Yes, sir, there was
So
a slight.
let us continue. The FT boundary is very simple. It is parallel to the FT vector, so it is FT boundary. Now, the last boundary to plot is this FA boundary. We know the boundary must be east-west trending, and it will be occurring exactly halfway between A and F plane. So, this is the FA boundary. Symmetrically spreading, though oblique, halfway between A and F running east-west. You see, there is no way the three plate boundaries, whatever AT boundary you choose, either these or that, the three plate boundaries are not meeting in the velocity space, so the triple junction is not stable. We come to an arbitrary situation. This is an ultimate test of our understanding of the velocity vectors, which is quite possible, and time permitting, I'll show a real case, where we are playing with two plates, A and B. A plate is fixed to the earth. A plate will not be moving. And the peculiarity of this situation is that, which is not very unusual in nature, is that the boundary between A and B in the eastern side is a north-south
Excuse me,
trend.
sir. Excuse
Yes, babe?
Sir, the pointer is not visible.
Okay, I bring it back.
Yes, sir, now it is visible.
So, okay, again it is gone. No, it is moved. So A plate is fixed. The boundary between A and B in the west is a north-south trending ridge. The boundary between AB in the east is a north-south trending trench, subduction zone, and the upper plate is A, that means B will be going underneath. The boundary AB in the north is a sinistral transform, that is a transform joining a ridge and a trench, and the same transform in the south, obviously, will be dextral. We have given the velocity of B plate with respect to the rift is about 100 kilometer per 10 million year. That means 10 kilometer per million year or 10 millimeter per million year. So the full spreading rate, that is between A and B, will be twice the half spreading rate, will be 200 kilometer per 10 million years, 20 kilometer a million year, or 10, 20 millimeter a year. We have marked 2 points on B plate as a star and a diamond. The question is, what will happen 10 million years from now? If one can come back at 10 million years, when the present will be 10 million years, how will it evolve? Let us look at the velocity space first. A and B, as we see, B is moving to the east, so B is moving to the east. By this much amount per 10 million years, I have used the scale of 10 million years so that it can be drawn a long way. The boundary between A and B is a rift. It will be halfway between A and B, and this is the rift AB. The boundary between A and B in the east is a trench, and A is the overriding plate. Obvious, this is it. On A, north-south trending, the trench. The two transform faults are the same to the velocity space thing. They will be passing through the velocity vector AB. One will be dextral, other will be sinistral. The moment you draw the velocity space, you come to a very interesting conclusion. What you see, that with respect to A, the rift will be moving to the east. Trench will remaining the same on the A plate overriding, but it will be moving away from it. That means, if you come back in future, A being fixed, the rift will be moving somewhere here. With time, it will be gradually moving to the east. And at the same time, the rift will be spreading and the material will be subducted through it. This is what exactly is shown in the second diagram. 10 million years from now, if I are looking at it, what you will see, this has moved the rift from A plate by this much amount, up like this. And how it has moved? By adding material to it. the new growth of plate. So this area was formerly covered by B. Now the boundary of the B has moved to the east, and this is the new material added. And the trace, so there is no transform fault here or there, and its traces are marked by the fracture zone. These are the isochrons, line joining points of equal age. So because they are spreading symmetrically, they will become older this way. You see, the diamond got subducted. If you allow another 10 million years and you come back and you see, following this dictum, the ridge is moving to the east. So we are gradually destroying the B plate and say, what will happen? What will happen in, say, about 6 million years from this 20? You will see the ridge has come here, the B has got completely subducted, and the whole tectonic process stopped because now it's a single plate A, there is no B plate, and there is no velocity space. And if you look geologically what is happening to B, the B will get detached as it go down and sink into the mantle. These things are not very uncovered at all, and these detached portions of B-like plate creates a lot of interesting feature in the mantle, whether they melt or not and when do they stop. So this is a fantastic example where you can join trenches and rift and you can predict the evolution. This is no story. You can see it in real life. This is, by the way, South America. This is the South American plate. If you go to the Scotia's plate, which is about 60 degrees south, this is it. I show you a very simplified high school level map of this plate. I am showing you only this much area just to bring out the point. This is a trench dipping to the west. This is a mid-oceanic ridge separating Scotia plate with Sandwich plate. You watch the latitude 60 south, very close to Antarctica. Antarctica Peninsula comes somewhere here. And you see what will happen. The model that we showed, and this has one difference. What was that? In the model, the trench is dipping in that direction. That means in this scenario, the Scotia plate will be gradually getting subducted and finally disappear. Because the subduction zone was dipping like that, and the sandwich plate is going underneath the South American plate. But in this case, the reality is the other way. The sandwich plate is in the overriding plate, and material is spreading here. So what will happen? The new material is added to it, and the trench will be pushed back. That means the sandwich plate will increase in area. In our previous case, the B plate was getting destroyed because it was getting subducted. Trench being attached to the upper plate, as material is added here, trench will move and consume the South American plate. By the way, there is a triple junction here, which is an R, rift junction, and it is a orthogonal spreading ridge, so this is a very stable triple junction. An experimental scenario, back to two plates, but with three boundaries now between two plates. Two plates A and B, with a transform boundary parallel to this. This is the transform boundary AP2. There is a trench in the north, which has P as the upper plate, AP1, the dentition in the upper plate, and AP3, the other trench in the southern end, with A as the upper plate. So what will happen? Let us draw the velocity space. Quite obviously, this is a subduction zone. So A is moving in that direction, P is moving in that direction. That means this is a dextral transform. A is moving in that direction, P is moving in this direction. So A is moving northwest, P is moving southwest. So in the velocity space, A will be here, P will be in the south. And velocity space is easy to draw because there is a transform for it to be parallel to it. Where will you plot AP1? P is the overriding plate. So in the velocity space, I plot the point AP1 here. This is the trench, AP1. And AP3, where A is the upper plate, so it passes through this with the A plate. And this is the transform fault. In the velocity space, what we see, AP3 is occurring to the northeast of AP1. That means AP3 will be moving to the northeast with respect to AP1 and vice versa. Interestingly, in true space, AP3 is occurring to the south of AP1. So when AP3 will be moving to the northeast, in future, AP3 will be from this position, will come here. Same thing with AP1. AP1 has to move south. So from previous positions in future, AP1 will move like that. So it will be a very interesting scenario where this boundary AP2 will transform, which become shorter and shorter in length in future with time. But still it is remaining dextral. There will be a time when there will not be any AP2. Here, AP3 and AP1 have touched each other. So it is the same two plate, but the direction of subduction is just the opposite. Here, P is getting subducted under AP3. Here, A is getting subducted under AP1. But the process moves on. As long as the velocities remain the same, AP1 has to move south. So in more future, AP1 will move south, AP3 will move north. So we will get the rebirth of the transform AP2, but with a change scenario. Now it will become a sinistral one because here A was occurring to the left and P was occurring to the right. Now here, after this point, the sides are switched. P is occurring to the left, so it is a sinistral. Don't think that these are just simple imaginary models. Let us take a quick look. I think I'll take another 15 minutes if I'm allowed to. Let us take a trip. We are here to far, far southwestern Pacific, New Zealand. Here we see New Zealand is marked by presence of two subduction zones and one strike-slip fault, a transform fault. We look at a plan view from the sphere to two-dimensional Spain. This is North Island, this is South Island, main constituent, this is Stewart Island. This is the Southern Alps, and this is a transform fault marking the boundary between Australian plate to the west and Pacific plate to the east. The story does not end here, it goes there. Then there is a trench, Hikurangi Trench, where the Pacific plate is getting subducted. That means the New Zealand is the overriding plate underneath Australian plate. And there is Pasagor Trench, where the polarity has reversed. The same two plates, Pacific plate and Australian plate. Now, the Pacific plate is in the overriding side, and the Australian plate is getting subducted. It's a very strange country. The northern island, where the capital Auckland is in the Australian plate. Whereas the southern island, thanks to test match venues, we know there is Christchurch, there's Dunedin, it belongs to the Pacific plate. So the two islands are plates apart. Now, what we look at it here, the opposite polarities of the trenches. Take a three-dimensional view. This is the North Island, we sliced it. This is the South Island, we sliced it. This is the Alpine Fault. North end of the Alpine Fault is the Hikurangi Subduction Zone, where the Australian plate is overriding plate and Pacific plate is getting subducted. Just the reverse scenario at Pasagor, where you see the Australian plate is getting subducted and Pacific is the overriding plate. And look at the Alpine Fault, it is almost vertical, a strike-slip fault, a transform, a plate boundary, and which is a dextral strike-slip, is moving like that. Make it simpler. Two islands, three plate boundaries, a transform fault, a trench with Australia as the overriding plate, a trench with Pacific as the overriding plate. Because these are subduction zones, we know the Australian plate is moving in that direction, Pacific is like that. So this is the dextral transform Alpine Fault. Very interesting scenario. Well, let us draw the velocity space. Very easy to draw its orientation because there is the transform. So it is like that. What plate will be here? we see the Australian plate is moving northeast, Pacific plate is moving southwest. So Australian plate will be plotted here. And Pacific plate is plotted there. That means Pacific is moving southwest. Australian plate is moving northeast. Where will you put this Hikurangi subduction zone? This is an interesting question. Where will you put that? We see the overriding plate is Australian plate. That means the trench will be attached to the overriding plate, that is Australian plate. So it must be drawn through here. Well, we have already plotted the transform fault here, and that is the velocity vector parallel by definition. So this is the transform fault, the boundary AF1, and then back to the northeastern trench, Hikurangi trench, which is attached to the Australian plate, the overriding plate like that. Now about the southern trench, the Pasago trench. Note this was Hikurangi overriding plate. Here it will be attached to Pacific plate. So this is one. Again comes a very interesting scenario. In the velocity space, the PS trench is occurring to the south of Hikurangi. So with time, the distance between the Pasago and Hikurangi will increase. So in future, we'll see the lengthening of alpine fault because the two trenches will be moving away from each other. If that is the situation, if we go back in past, what do you expect? In future, the distance between Hikurangi and Pasago will increase. So in the past, what was it? These 2 points must have been closer to it because they had to move to the north and to the south to come to this present configuration. So if you go a little past, you see the two trenches are closer to each other. And with time, they moved away. If I go even more deep past, well, the alpine fault is gone. The two trenches are continuous with opposite polarities. It is not stopping here. But you know, these were constantly in future moving to the north. So in back projection, they will be in a much more south positions. So if you go even more past, Hikurangi were far to the south of Pasago. A major changes happened after that. We have the rebirth of the alpine fault, but now it is a sinistral one. So we have Australia plate is always moving to the north and Pacific plate is always moving to the south. But now the Australian plate and Pacific plate, you see, the Pasago is attached to Pacific plate. So this is where it is attached to. And Australian plate has the Hikurangi attached to it. So they have switched positions and that changes in the polarity of the strike slip movement. So the transform fault, which is now dextral, was sinistral. Nobody can claim this has happened. So people will say at one point, this is the scenario, then it becomes like that, then it becomes like that. So a sinistral fault changed into a dextral, started lengthening, it come here, come there. Nobody can prove it exactly because the fun with this thing is that the two islands belong to two plates. But if you look at the geological data, paleomagnetic data, we come across a situation 10 million years before present. We see the alpine fault and we see the western part of the South Island and eastern part of South Island. And they predict that yes, the northern part, northern island, western part has moved north to come to the present configuration. So it is quite a possibility that alpine fault has an evolution as predicted from the model. I can cite a case, but tell me the organizer, how many minutes we have? Hello?
Yes, sir, you have time. You can speak.
Okay. So what we do, I put forward another case where these two-dimensional vectors are the key to solve a problem. We were here in the western side of the Pacific. Now we go to the northwestern side. We can see a plate boundary here on the northwest coast of North America. This is the plate boundary that we have shown you here. This is North America. This is where the boundary between the USA and Canada. This is Vancouver Island. Somewhere here is Seattle. It is a long-standing observation of geophysicists that there is certain incongruence in the plate boundary configuration. This is the map that we had been prepared in early 1960s when plate tectonics in the state of development. And this is all observation of geophysicists. People found that there is a Mid-oceanic ridge, and everybody thought this Mid-oceanic ridge is separating Pacific plate from North American plate. Fine. Okay. But they found in the Mid-oceanic ridge, there are transforms which are not mutually parallel. This is a very interesting case. By definition, transform faults are exactly parallel to the movement vector. There are magnetic anomalies here. With the help of magnetic anomalies, geophysicists measured the relative velocity of North American plate is of the order of 58 millimeter a year in this direction, say about 100 degrees. This is the end of San Andreas Fault here. This is Mendocino fracture zone. And from the San Andreas Fault, we know the velocity between Pacific plate and North American plate is 56 millimeter a year, but more to the south than this one. They also found that the velocity between North America and Pacific is the same as here and there. This is Queen Charlotte strike slip fault transform. But the problem arises non-parallelism of this transform with this, and same two plates, Pacific and North America, within 100, 200 or 500 kilometers, having two different velocities, which is impossible because the basic concept of plate velocity is in two-dimensional vectors. You cannot change the vectors, then it will not be. You cannot have on the velocity space 2 points giving you two different velocities. So people started drawing the velocity triangles. This is the first attempt, and people thought, Pacific being such a big plate, I'll put it in origin and we'll calculate the relative velocities. They use the velocity between Pacific and the other plate as 58 millimeter a year, and they plotted in the velocity space. They used this San Andreas transform, measured its velocity and plotted from Pacific. And see, these two vectors are not parallel. So it clearly showed what we call North America here and what we call North America there are not two identical North Americas. They are different plates. So there must be a boundary between this so-called North America and this so-called North America. And this is the boundary they later found by detailed surveying of a submerged trench and structures that relate to deformation along trench. So they have redrawn the boundary. They kept North America as constant. This is Pacific plate, moving to the northwest from San Andreas Fault. And they named it Farallo plate, which is the remnant of a huge plate that is older than the Pacific formed by breakup of the Panthalassa. When Farallo was there, there was another plate called Kula, which has disappeared. So this is the Farallo plate moving like that. So what it predicts? North America is moving to the southwest, Farallo plate is moving to the northeast. Farallo plate is moving to the northeast. So NVF, relative velocity of Farallo with respect to North America, is 26 millimeter a year. That means 26 kilometer a million year. So that is a subduction zone. Well, that is a submerged tent. Then all of a sudden it occurred to the minds of the scientists. Well, there is a series of volcanoes. In California, there is Mount Shasta, a beautiful peak. Then in Oregon, you have this famous Mount St. Helens, famous for his 1972 eruption. Those who go to Seattle look at Mount Rainier, the tallest mountain in the USA, mainland USA. Then you have Mount Hood and other things. So there is a series of volcanoes only around this line up to this point. So just by using a velocity triangle, they proved the existence of a mystery plate which has eluded all the geologists and geophysicists till about mid-1960s. So this is the power of using two-dimensional vector along the plate boundaries. One of our ex-students, very enthusiastic, having a very interesting habit of hunting down interesting papers from the web and raising very important questions, throwing them at the professors, sent me amazed that the processes that I have developed, understood and developed, started in mid-1960s and matured in 1980s. And he pointed out to me, it's unbelievable. The same old thing is being used in 2016, that in a paper which is a junior edition of Science Advance, to explain the birth of Pacific. And I show you the diagram they have used, plate velocity vectors on 2 dimension with different kind of plate boundaries. Time permitting, someday we'll be talking about that. My talk is based on material collected from many different places, but almost all the diagrams have to be redacted for this purpose. And these are the landmark articles that rewrote the history of geology, if not science. These are 2 are the Bibles of plate tectonics, Morgan 68, and then McKinsey and Parker 67. McKinsey and Morgan developed everything that has to be developed about the geometry of triple junctions. And this is another magnum opus from this lady Tanya daughter, who explains on Andreas Fault and Dickinson and Sider also. And if you want to learn this thing, almost following a teach yourself book, please consult this one by Cox and Hart. He was a Stanford professor and one of the just architect of Cenozoic paleomagnetic stratigraphy and magnetochrones. This is the one. So this pretty much covers the things I thought I would be able to cover. Maybe I was a little too fast. I apologize for that. And it gives me a very creeping sensation. I cannot see your faces. I cannot measure how dejected you are. The talk is about vectors, and I talked about vectors and arrows. So my innate fear now is that whether my arrow has failed to reach the target. And who else I can depend on to express my feeling rather than borrowing from the great Shukumar Rai. And he says, oh my God, what is this? I aimed at something. I aimed at possibly hitting something else. So instead of adding possibly we inflicted injury, my apologies for that. Thank you.
Thank you, sir, for such an interactive session, and it was wonderful. And it definitely it would be immense helpful for our future and academic career. Sir, we have some questions from the participants. I would
Sure.
request you if you take those questions. We have gathered few
Sure.
questions from the question we have received.
Sure,
The
go
first,
ahead.
okay, sir. The first question is from Shiva Teja. He has asked how we can estimate the rate of plate movement and which factor affecting the movement of plates.
Okay. Well, firstly, the way the plate tectonics was developed, it was not aimed at what moves the plate. So what factors moves the plates will be another discussion. Plate tectonics is more about kinematics, the geometry of the plate boundaries, and what kind of movement the plates are taking place. Your question is very pertinent, but it is a part of plate dynamics, and for that we have to go deeper into the mantle. What exactly makes the plate move? Well, convection currents play a major role, but since about 2,500 billion years back, the plates are moving with their own inertia. And it is said that the pull in the subduction zone, the subducting plate being very dense, they pull the plate behind it and drives the plate tectonics. That is another issue. Plate vectors initially were measured in the ocean from the separation of oceanic magnetic anomalies. In a rift, we symmetrically add material on the 2 sides of it, and this basaltic material having iron-bearing minerals, magnetites and other. These magnetites record the then paleomagnetic field. And we know, at least in the Cenozoic, the magnetic field reverses quite a number of times. So by measuring the reversals, we correlate the two magnetic bands on two sides. Say we have a mid-oceanic ridge. Immediately to the east, there is a normal magnetic band to the west, and then it ends at a boundary, say about 100 kilometers from the ridge, and a reverse polarity starts. So distance between these two bands, one in the east, the other in the west, where the magnetic reversal is recorded, we measure the distance, and as I said, the Doyle, Cox, and Dalrymple, the trio, who measured about 30,000 basalt sample to figure out the age when the magnetic reversal took place by dating those basalts. So we know the age of these bands, and we know how wide they are. That gives us the spreading rate. That is paleomagnetic. But nowadays, except in the deep ocean, it becomes very simple to measure it with high-powered GPS. And there are plate movement vectors velocities that can be measured called VLBI, very long-range interferometry, very long base range, VLBI, very long base range interferometry, where Earth-based station measured the time of arrival of pulses from pulsars. And we measured the same pulse in two different periods of time at two different places, and difference in the time of arrival is calculated. It is said with that kind of mechanism, over a year we can measure the change in distance between Calcutta and New York if it is more than 2 millimeters. So such is accuracy. But now the most easy, affordable method is putting GPS stations in two different places and measuring the change in distance over time, and they can be measured over intervals of year, and they are now very, very close to the accurate values. Yes.
Thank you, sir, for answering the question. Next question. Next question is from Ankita Rajput, AMU. Is Euler's theorem of plate tectonics the same explained by the plate tectonic vectors?
Euler has no theory on plate tectonics, okay? Euler was a genius. So he only said, if you rotate something around on a spherical surface move, it will have a rotation axis. With the plate tectonics, people use it when you try to explain the movement of plates. When you make one plate move over the earth, it covers a curved line. Say we have a plate, think about India. India was, say, about 125, 200 million years back, was very close to the position of Australia or even South. Now, over these last 200 million years, it covers from a position of nearly 60 degrees south to about 23rd degree north. So it is a huge journey of about 60 degrees. If we think it is a single straight path, then it has rotated around an axis which is running east to west, almost passing to the equator. So because the path covered by Earth is an arc on the Earth's surface, so the center of the arc, and you draw a perpendicular line to the center, that gives the pole, and we call it Euler pole to distinguish it from the pole, that is the pole of rotation of the Earth or magnetic pole. We use the theorem of Euler to calculate these angular velocities on the things. As I said, when you look at two dimensions, well, as I said again, in hundreds of square kilometer, Earth's surface is flat. And the plate boundary areas are seldom wider than that. So there the movement between the two plates can be easily analyzed using two-dimensional vectors. Okay?
Sir, next question is from Shumana Roy, MSc IIT Roorkee. What is the scenario in the same supra-subduction zone?
In the what supra-subduction zone?
What is the scenario in the same? Is it?
Same means what?
Uh,
I don't understand that. Same supra-subduction zone, I cannot understand what is same.
What is the scenario in the supra? Actually,
Not same. What is the scenario
Okay.
in the supra
In
subduction?
the supra-subduction zone. Sorry, sir. Yeah.
Okay, I like to know that what he means by supra-subduction zone. If he is asking about petrology, I don't think I should discuss it here. That's a very interesting subject, okay? And you can ask the same thing to Dr. Ghosh, the supra-subduction zone, but it has nothing to do with the geometry of movement. The geometry says there is a subduction zone, and using the geological information, it includes in the model where will you put the trench. That's all it does, okay? It does not go beyond the skin of the plates to explain what is. I repeat again, at our level, at the classical level of plate tectonics, it's a kinematic theory. It first analyzes the movements, relative movements of the plates, and how these movements are controlling the surface geology. So a plate tectonician will say, if the two plates converges and one plate goes underneath, then I say the overriding plate will have all the features that you see in a subduction zone, volcanic arc, if there be any accretionary wedge or back arc, and etc. But that is not the subject matter of the plate tectonics in the classical sense.
Okay, sir. Sir, next question is from Dibbajati Chaudhuri, JRF, ISAR, Kolkata. He has asked, in slide 30 and 31, if the position of plate B and C are switched and the transform is a sinistral fault, would that have changed my velocity vector diagram?
No, the velocity vector will not change. I need not have to show you that. As I said, as long 2 points maintaining the same velocity between them, the velocity space will remain the same. Velocity space has no room for the position of the points, the actual objects. When you plot 2 points on the velocity space, their relative position says only their relative velocities. There is no difference. Can you see my 2 fingers? Tell me, we compare. Can you see my 2 index fingers?
Yes, sir.
Okay. What I am saying is that my right hand has a velocity to the right. Can you see that I am moving it to the right?
Yes, sir. We can see.
You just confirm when I ask. My left hand is moving to the left. So when I plot these 2 points, the fingertips in the velocity vectors, the right will be pointing to the east of the left point. It is moving to the... Now, if the two in actual scenario, my right hand is to the right of the left hand, my left hand is to the left of the left hand. So the velocity space says that if this is the true space situation, then the distance between my 2 fingers will gradually increase with time, because the right hand is occurring to the right of left. But you see, the velocity space has not changed. I am following the velocity space where I am moving my right hand to the right and left hand to the right. Now look at this scenario. I have crossed my hands. Now my right hand is to the left and my left hand is to the right. What the velocity space says? It says my right hand must move to the right and my left hand must move to the left. So now what will happen? The 2 points will come close to each other and will simply move past. If it is moving past, then it will change like that. Could you understand what I am saying? So the velocity space, we cannot change. The moment we change the velocity space, we have to reconstruct the whole plate tectonics regime, because the velocity between 2 neighboring plates will change and the plates are interlocked over the sphere. So changing between any pair of major plates will affect every other plate. So as long as the velocity space remaining the same, the 2 plates may move past each other, may come, may go away from each other, as long as they're moving along the velocity line with the same relative velocity. So changing from sinistral to dextral, if I look at here, as long as P is occurring here and A is occurring there in the velocity space, A must be moving to the northeast and P must be moving to the southeast. So when I go to the change scenario, we are following the same. You see, the PS attached to P is here and HK is attached to A is there. So what is happening? HK is moving to the south and this is moving to the north. So there is no change in the velocity vectors, velocity space, but the plates have switched sides. Just like this mid-ocean ridge scenario. Just these two diagrams. Here it's a fault, transform fault with the blue on the northern side, green in the south. By the velocity space, blue must move to the west. So blue is moving to the west, green is moving to the east, so it's a left lateral transfer. When the plate boundary, plate switch changes, just switch the places. The blue and green, their relative velocity vectors are the same. Green is moving to the east, blue is moving to the west. So now what is happening? Compared to the earlier situation, now the green plate is to the north of the blue plate. So the green plate has to move to the right, east, and blue plate has to move to the west. So it will become a dextral transform as opposed to same velocity space, same scenario, a sinistral transform. Okay.
Okay, sir. Sir, our next question is from Shushovan Nyogi, GSI. When we are talking about subduction, why we are considering only two dimensions? Because the plate must have a velocity in z direction.
I'm not sure what you mean by z direction. I am talking about two-dimensional space, and if you say xy, plates are moving on a plane. Plates do not have on the surface a vertical motion. The vertical motion of plate does not affect the plate tectonics as it does not affect the velocities or relative velocities between two plates. I can thicken a plate, make it thicker, so it will go thicker, but that does not affect its relative velocity with respect to the neighboring plates. So the vectors that we are doing, even if you do it in 3 dimensions, the rotation, instead of saying AVB, we say A omega B. It has 3 components to it. The position of the latitude and longitude of the pole and the angular velocity with respect to the pole, that is the magnitude of the angular velocity, and the direction of angular velocity while looking down the pole, is it clockwise or anti-clockwise? So the moment the plate goes underneath another plate in a subduction zone, the plate tectonics as vectors has nothing to do with that. Because the movement that we analyze is always on the surface of the plate. So if you implied Z is the vertical direction, there is hardly any movement compared to its horizontal velocities of plate. When you are under thrusting one plate over another, it is only near the boundary you are putting that, not deep inside it. That's why in the subduction zones, we get mountains, not deep inside. So there is hardly any effect on the third dimension, be it considered as a 2-dimensional vector, be it considered as a 3-dimensional rotational thing. It has no effect in the third dimension.
Thank you, sir. Sir, next question is from Jyotirmoy IISA. The question is, when alpine fault in New Zealand had 0 length and 2 subduction zones were formed in reverse direction side by side, what was the state of mantle convection below this region?
Very difficult to say. You are modeling mantle convection, maybe you will be able to say that. I tell you one very important aspect of it. When Earth was hot, as per my reading, it could drive the plates above it. One fundamental problem with the Earth is that the convection specialists, the physicists, they analyze mantle movements and they say there is absolutely fine. The mantle is convecting and it is obeying all the rules of convection. And one of the rules of convection is that usually the convecting layer on its two sides is bounded by two convecting layers. So convection is a way of transferring heat from the lower convecting layer to the lower conducting layer to the upper conducting layer by the method of convection. An ideal convection, which is impossible in case of earth, is something is very important, that the entire convecting layer attains a uniform temperature. So there won't be any geothermal gradient, it will be a vertical line. So that the amount of heat input from the conducting layer below will be the same as heat output from the convecting layer to the over-rising conducting layer. This is the ideal case. Usually it does not happen. So assuming this is not happening, and assuming, unlike a true convection, not assuming is a fact, that mantle itself generates a heat by radioactivity. So it's much more complex. With all these things taking into considerations, the hardcore physicists and geophysicists, not just geologists, have no problem with this plate tectonics, because the lithosphere is a conducting layer above a mantle which is convecting. The fundamental problem with geophysicists is how to explain the bread and butter of the plate tectonics people. They can imagine there is a conducting layer on top, the lithosphere, okay, the rigid layer conducting, dominantly except from the last few kilometers. But what has broken down the lithosphere into plates? They have no answers to it. They believe the down oilings are very important once there is a down oiling, that is subduction zone. And the up oilings that we think we are in the mid-oceanic regions also subsidiary. But they are at a loss how to break. The convection theories do not explain how to break the lithosphere into smaller plates. There are all kinds of ideas, meteorite impacts, and there is Barkovici from Yale. He has very strange ideas about the phase changes within the lithosphere, making one portion of a continuous lithosphere denser than other thing. So back to your things again. Till about 2,500 million years, Earth was hot enough to carry the lithospheric plates on top of it by its convection. After that, Earth has cooled and it has done two major things. They have slowed down the rate of convection in the geological scale, and the lithospheric plates has become denser. So you have denser plates that has to be moved. It's very difficult to do that. Now, because before 2,500 million years, even those who challenges early plate tectonics, they agree that after the Middle Archean, these similar processes of plate tectonics was operating. So there are subduction zones that are pulling the plates. Okay? And these subduction zones, because the lithosphere which is subducted is too dense and too cold to be melted, and people believe the earliest lithosphere which got subducted is still kind of resting there on the core mantle boundary. People question this, but there are a lot of agreements on that. So it is the negative buoyancy of the subducted plate that pulls the plate into the subduction zone. So now it is said in the upper part of the mantle, the subduction is controlling the convection. The other argument is that there are places where the ribs are moving away. Think of the boundary around the Antarctic plate. Antarctic plate is more or less fixed in the South Pole. And there is though very slow spreading ridges around Antarctic, but the ridges are spreading. So where will it go? That means that Antarctica being fixed, so the ridges are moving away. And at the same time, these up oilings are moving away. Had it been controlled by mantle convection, it would have affected the mantle convection everywhere and could have made a big change. So now people more or less would agree that after 2,500 million years, the upper part of the convection is controlled by the drag of the plate tectonics. So when you have two opposing polarities of a trench, one is dipping to the north, so one is dipping to the, say, west, the other is dipping to the east, and the trench is continuous. I will say the convection will be just following the downgoing slabs. By no means it is going to change the story elsewhere. So there is hardly any problem with that. You can see similar situation. If we have time, I can show a very interesting scenario. Am I taking too much time compared?
No, sir. No, sir. You can.
If you get bored, you can tell me, because I am closing
No,
on
sir.
65, so I like to talk.
No, sir. You go ahead, please.
Okay. If I have the slide, I'll show you the person who asked me this. The situation I described is not that unusual. Oh, I didn't bring it here. Yes, look at here. This is Japan. Very interesting place. It has two triple junctions, none of them are stable. One is Fujiwara and Bozo. Look at here. The eastern boundary of Eurasian plate. Here, the North American plate is the overriding plate. You cross this Bozo triple junction, the Fuji triple junction. Now, the same Eurasia plate, which was under thrust there, is now the overriding plate. So a very interesting thing is happening here. Here, the North American plate is eating Eurasia plate, whereas here, the Eurasia plate is eating Philippine plates. So these are not very, this is quite in contrast to the eastern boundary, where Pacific plate is getting under thrust, Pacific plate is getting under thrust, though the two overriding plates are different. Here, the same two plates, once this is the under thrust, and once this is the under thrust. So we don't have much time, so otherwise we could have analyzed it with the vector triangle. So that is not very useful. That also, again, goes to prove that it is the drag of the under thrust plate that conducts it. That's why it is now believed that it is the drag of this subducting plate that starts the convection and controls it. The upwellings is only to balance the mass, so they are not fundamental. And we still do not have answer from the geophysicist why the plates were formed by breaking off the lithosphere. Anyway. Any more questions? Hello, compare.
Okay,
Can you
sir.
hear me? Yes, go ahead.
Okay, sir. The last questions. The last question is from Piyush Sadhu Khan, GSI. What is the scenario of Juan de Fuca plate? How did it disappear and San Anderson fault evolve?
Okay, this needs another half an hour talk. If they are ready, I can give you a talk to explain that. But what I can say here is that, if I can show you the slide. This is very quickly the San Andreas Fault. This is Baja California. Okay, just to get ourselves located, this is where Los Angeles, this is San Francisco, this is Vancouver, and this is Baja California, and this is the San Andreas Fault, west coast of US, textile fault. This is the 1D Fuca plate, this is Pacific plate, this is North America plate. The San Andreas Fault is a very interesting structural feature that shows the interaction between three plates. The San Andreas Fault ends here. You see the same strike of San Andreas Fault, a dextral changes into a subduction zone where 1D Fuca plate is getting subducted. Very simply, 1D Fuca plate is getting subducted because the rate of subduction across this trench called Cascadia Trench is much higher than rate of generation of 1D Fuca plate across this mid-oceanic ridge. So what will happen? The more and more of the plate will subduct it, and that has been happening for the last 38 million years. And 1D Fuca is gradually simply disappearing. Very quick cartoon shows this. This was the three-plate scenario we have been talking about. This is the Pacific plate. This is the Farallo